Today we're going to explore solving quadratic equations that have complex solutions. This is a powerful technique that expands our ability to solve equations beyond those with only real number answers. Let's examine this specific quadratic equation, 3x squared minus 2x plus 1 equals 0. This particular equation will lead us to complex solutions, as we'll soon discover. Before solving, we need to identify the parts of our equation by comparing it with the standard form of a quadratic equation, x squared plus bx plus c equals 0. This standard form is the foundation for using the quadratic formula. Looking at our equation, we can identify that a equals 3, which is the coefficient of x squared. This value tells us about the opening direction and width of the parabola represented by our equation. Next, we identify that b equals negative 2, which is the coefficient of our x term. This value affects the horizontal position of the parabola's vertex. And finally, c equals 1, which is our constant term. This value determines where the parabola crosses the y-axis. Now that we've identified all our coefficients, we can apply the quadratic formula to solve this equation. The quadratic formula states that x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This formula gives us both solutions to any quadratic equation. What makes this particular equation interesting is that when we substitute our values, the expression under the square root will be negative. This is what leads to complex solutions, where we'll need to work with the square root of a negative number, introducing the imaginary unit I. When solving quadratic equations, we first need to identify the coefficients. The standard form of a quadratic equation is a x squared plus bx plus c equals 0, where a, b, and c are constants. Let's work with this specific quadratic equation, 3x squared minus 2x plus 1 equals 0. To solve this equation, we'll first need to identify the values of a, b, and c by comparing it to the standard form. In the standard form, a is the coefficient of x squared. This is the number that multiplies the squared term, representing the steepness of the parabola when graphed. Looking at our equation, we can see that the coefficient of x squared is 3, so in this case a equals 3. The positive value tells us that the parabola opens upward. Now that we've identified a, let's move on to finding the value of b in our equation. In the standard form, b is the coefficient of the linear term x. This term affects the horizontal position of the vertex of the parabola. In our equation, we see that the coefficient of x is negative 2. Therefore, b equals negative 2. The negative sign will influence the direction in which the parabola is shifted. With a and b identified, we now need to find the value of c to complete our set of coefficients. In the standard form, c is the constant term, the term without any variable. This constant determines where the parabola crosses the y-axis when graphed. Looking at our equation, we can see that the constant term is positive 1. So c equals 1. This means that when x equals 0, the value of the quadratic expression would be 1. Now we've successfully identified all three coefficients for our quadratic equation. We have a equals 3, b equals negative 2, and c equals 1. These values are essential for using the quadratic formula to find the solutions, which will tell us where the parabola crosses the x-axis. Let's calculate the discriminant for the quadratic equation 3x squared minus 2x plus 1 equals 0. The discriminant will tell us important information about the nature of the solutions to this equation. For any quadratic equation in the standard form, ax squared plus bx plus c equals 0, the discriminant is given by b squared minus 4ac. By comparing our equation 3x squared minus 2x plus 1 equals 0 with the standard form, we can identify that a equals 3, b equals negative 2, and c equals 1. Let's substitute these values into the discriminant formula. First, we'll calculate b squared. Since b is negative 2, b squared equals negative 2 squared, which equals 4. Next, we need to calculate 4ac. We have a equals 3 and c equals 1, so 4ac equals 4 times 3 times 1, which gives us 12. Now we can find the discriminant by subtracting 4ac from b squared. That's 4 minus 12, which equals negative 8. The discriminant is negative 8. This is a crucial finding because the sign of the discriminant tells us about the nature of the solutions to our quadratic equation. A negative discriminant indicates that the quadratic equation has no real solutions. In the quadratic formula, x equals negative b plus or minus the square root of the discriminant, all divided by 2a. When the discriminant is negative, we need to take the square root of a negative number, which leads us into the realm of complex numbers. Here on our number line, we can see negative 8 marked in red. The square root in our quadratic formula requires us to find a number that, when squared, equals negative 8. But in the real number system, all squares are positive, so there's no real number whose square is negative. To solve this problem, mathematicians introduced the concept of an imaginary number I, where I squared equals negative 1. This allows us to extend our number system into a two-dimensional plane, with the horizontal axis representing real numbers and the vertical axis representing imaginary numbers. Using the properties of imaginary numbers, we can express the square root of negative 8 as 2 times the square root of 2 times I. This is because we can rewrite negative 8 as 8 times negative 1, and then take the square root of 8 multiplied by the square root of negative 1, which is I. This negative discriminant is telling us that our quadratic equation 3x squared minus 2x plus 1 equals 0 has two complex solutions, which are complex conjugates of each other. These solutions will be of the form alpha plus beta I and alpha minus beta I, where alpha and beta are real numbers. The complex solutions may seem abstract, but they are incredibly useful in various fields of mathematics, physics, and engineering. The quadratic formula is our key tool for solving quadratic equations. It states that for any equation in the form ax squared plus bx plus c equals 0, the solutions are given by x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. For our specific quadratic equation, we've determined that a equals 3, b equals negative 2, and c equals 4. Substituting these values into the formula, we get negative b equals 2, since the negative of negative 2 is positive 2. For the discriminant, b squared minus 4ac, we get negative 2 squared minus 4 times 3 times 4, which simplifies to 4 minus 48, or negative 8. So our expression becomes x equals 2 plus or minus the square root of negative 8, all divided by 6. Now we encounter the square root of negative 8, which doesn't have a real number solution. This is where complex numbers come in. We can rewrite the square root of negative 8 as the square root of 8 times I, where I is the imaginary unit defined as the square root of negative 1. We can further simplify the square root of 8 as 2 times the square root of 2, making our expression 2 times the square root of 2 times I. We substitute this simplified form back into our equation. Our expression is now x equals 2 plus or minus 2 times the square root of 2 times I, all divided by 6. The numerator has two parts, the real part, which is 2, and the imaginary part, which is plus or minus 2 times the square root of 2 times I. For the final step, we can simplify this fraction by dividing both the numerator and denominator by 2. This gives us 1 over 3 for the real part, and plus or minus the square root of 2 over 3 times I for the imaginary part. So our solutions are x equals 1/3 plus the square root of 2 over 3 times I, and x equals 1/3 minus the square root of 2 over 3 times I. Notice that these two complex solutions are conjugates of each other. They have the same real part, but opposite imaginary parts. This is always the case when solving quadratic equations with real coefficients that have complex solutions. Let's review what we've learned about solving quadratics with complex solutions. When the discriminant is negative, we use the imaginary unit I to express our answers in the complex number system. Our final answer shows that this quadratic equation has these two complex solutions. If we were to substitute either of these values back into the original equation, we would find that they indeed satisfy it, just as real solutions would. The difference is that these solutions involve the imaginary unit I.